Everyone. Welcome to our last session of our introduction to modular forms. And thank you for joining today despite the heavy rain and adverse weather. So yeah, let's start with what we did last time. So last time we defined the L function of a modular form. So let us recap that real quick. So let F be a modular form of weight K. Then we have seen that f of z can be written as a q series. It is a n q to the n runs from 0 to infinity. Yeah. Then we define the L function attached with this modular form like this. This is defined as yeah, summation of an over n to the s. But this time this sum runs from n equals to 1 to infinity. So yeah, so this L function sort of ignores the zeroth coefficient of the Q series. Yeah, and I think we proved that the L function absolutely converges for this LFS converges absolutely for like real part of S being greater than K, where K is the weight of the modular form. Right? Real part of S greater than K. Yeah. Yeah. Also, we have seen that the L function of the Eisenstein series is the product of two zeta functions. So L of ek, comma s. This is equal to negative 2k over bk zeta of s times zeta of s minus k plus 1. Okay. Yeah. So we have a hint that probably L function is has some deep connection with zeta function, right? And yeah, and last time we have seen a theorem which we did not prove, but today we're going to prove that theorem. So let us state that theorem. The theorem states that let f be a modular form of weight k, and of course k is at least 4, because we have seen that if k is smaller than 4, then modular forms of weight k are basically the zero functions. Right. So, and we define the completed L function like this, completed L function. So, completed L function of the modular form f, and that is defined as capital lambda of f comma s is equal to 2 pi to the power negative s gamma of s times the L function. Okay, so this is the completed L function. And the theorem states that this completed L function has analytic continuation. So initially the L function is defined in the half plane of half plane where the real part is greater than k, right? Initially the L function is defined here in this region. So the theorem says it has analytic continuation to the whole of C except for at worst simple poles at s equals to 0 and s equals to k. Okay. By at worst, we mean that, well, yeah, sometimes the completed L function has analytic continuation that is entire. But in the worst scenario, it has two simple poles. And the simple poles are at here and here. Okay. So since we have two simple poles, we can compute the residues. And the residues are residue of lambda at s equals to 0 is given by negative a0. And the residue of lambda at s equals to k is negative 1 to the power k over 2 times a0. So yeah, this result is actually really interesting because although the L function we define, the L function sort of forgets the zeroth coefficient of f. It actually remembers it. How does it remember? By the residue of the poles at 0 and k. Okay. Yeah. Yeah. Also, we have another functional equation for the completed L function that is given by lambda of f at k minus s is equal to -1 over -1 to the power k over 2 times lambda of f comma s. Yeah.
K is an integer, right?
Yeah, k is an even integer.
Even
Well, we proved that modular forms of odd weight are basically the constant zero functions. So the only interesting modular forms are actually of weight, even weight greater than or equal to 4. Yeah. Now we are going to prove this theorem. Yeah. If for that, let us first compute, let's first manipulate this part. This is, so proof that is 2 pi to the power negative s gamma of s L f comma s. Okay, so the L function is so 2 pi to the power negative s gamma s, and the L function is a sum of a n to the s, and this sum is n equals to 1 to infinity. Okay, so this is basically sum of a n over 2 pi n to the power s comma of s, and this sum is n equals to 1 to infinity, right? And there is an integral representation of the gamma function, so sum of a n 2 pi n to the power s, that integral is t to the power s e to the negative t. No, that is t to the s minus 1, right? Yeah. Okay, so we can take this 2 pi n inside the integral to get sum of a n integral of t over 2 pi n to the power s e to the minus t dt over t. Yeah. Now we're at, okay, I forgot to put the limits. The limit are 0 to infinity. Yeah. Now let us do a change of variables. That is, let's say y is t over 2 pi n, right? Then we get that dt over t is equal to dy over y, right? So this becomes sum of a n y to the s e to the negative 2 pi ny dy over y, right? Yeah. So, and now we are going to switch the order of integral and summation. So this becomes 0 to infinity y to the s minus 1 and sum of a n e to the negative 2 pi ny n equals to 1 to infinity. This is dy, right? Okay, so we can do this like we can switch the order of integral and summation in the region where real part of s is greater than k, because in that region this sum is actually absolutely convergent, right? And absolutely and uniformly convergent. So yeah, so we can do this in this region. Yeah. Now what is this? Does this look familiar? So f of z is basically sum of an, sorry, this integral should, this sum should be n equals to 1 to infinity. Yeah. F of z is an q to the n, and q is e to the 2 pi I z, right? N equals to 0 to infinity. So this term inside the parenthesis is actually f of iy minus az, right? So this is 0 to infinity y to the s minus 1 times f of iy minus a naught dy. Yeah. Yeah, now we can break this integral apart into two integrals, one from 0 to 1, another from 1 to infinity. F of iy minus a0 y to the s minus 1 dy plus 1 to infinity f of iy minus a0. Now, if y is greater than or equal to 1, then what is f of iy minus a0? So this is actually a sum, right? This is a sum of an e to the negative 2 pi ny, right? Yeah. And we can say that this sum is of order of e to the negative 2 pi y. Because as y increases, the latter terms contribute less and less. So yeah, so only the first few terms are like more dominant. So yeah, so this holds. Sorry. Yeah. So therefore, this integral right here, this integral converges because it's essentially the product of a exponentially decaying function and some polynomial. Okay, so this integral right here, it converges, and furthermore, this converges for all s in C. Okay, so although the while writing this term, we have assumed that real part of s is greater than or equal to k, actually greater than k. But then we found that it can be written as two sums, one of which converges for all s in the complex plane and is holomorphic. Yeah. So this term is taken care of now. Yeah. And this integral right here, we can write it as from 0 to 1 f of iy times y to the s minus 1 dy minus a naught is constant. So y to the s minus 1 dy 0 to 1. Okay, so this term is basically negative a naught over s. So now we are going to compute this term, this integral. So yeah. So for this as well, we shall do a change of variables, that is, we shall change y to 1 over y. So what do we get? We get f of I over y, which is actually negative 1 over iy. So I'm saying that I over y is actually negative 1 over iy, right? So yeah. And if we do that change of variables, what do we get? The upper limit still stays 1, but the lower limit is infinity. and this is f of negative 1 over iy. What is this? We know the definition of a modular form. No. The definition of a modular form says that f of negative 1 over z is equal to z to the k. Right. So, yeah. So, iy to the power k. So, what does that contribute? Negative 1 to the power k over 2. Then we have y to the k, f of iy times y to the minus s plus 1, right? And for this change of variables, we have a factor of negative 1 over y square, right? Yeah. Is that correct? Because we did this change of variables y to negative 1 over y. So 1 over y. Yeah. So this negative sign flips the limits. So 1 to infinity, negative 1 to the power k over 2, y to the k minus s, f of iy, dy over y. Right. Now what do we do? We throw in a factor of negative a naught here. So we get negative 1 to the power k over 2, y to the k minus s, f of iy minus a0, dy over y, plus negative 1 to the power k over 2, y to the k minus s, right? And the limits are 1 to infinity. Now, what is this integral? This is, well, negative 1 to the power k over 2 a naught, right? Then y to the k minus s minus 1. So that is k minus s times y to the k minus s, right? And from 1 to infinity. Yeah. So if the real part of s is greater than k, then as y goes to infinity, this vanishes. Wait. Right. So this is integral from 1 to infinity, negative 1 to the power k over 2, y to the k minus s, f of iy minus a naught dy over y. minus negative 1 to the power k over 2 a naught over k minus s. Yeah. And as before, this integral. So for large y, f of iy minus a0, this is of order e to the negative 2 pi y. And this multiplied with polynomial and taking this integral. This converges and is holomorphic for all s. Right? So therefore, sorry, like is this like this sign should be positive or negative? Yeah, this one.
This is positive. We separated it.
Oh right, yeah, this is positive. Thank you. Right. So we get that negative 2 pi to the power s gamma of s times the L function. This is equal to uh, let's collect all the terms. This term is a holomorphic function, so some entire term plus we had negative a0 over s negative a0 over s plus some other entire function which is this integral plus negative 1 to the power k over 2 a0 over k minus s. No, this sign should be negative because there is a positive sign for this integral and a negative sign because the limit. So when we plug in the limit, let's say y to the k minus s. For y equals to infinity, the infinity terms vanish, right? So the only remaining terms are of y equals to 1. So yeah, this term should be, this sign should be negative. Yeah. So, plus a0 over s minus k. Now it makes sense. Now looking at this function, so we can therefore say that the completed L function lambda of f comma s, this is almost entire, right? Because it's the sum of two entire functions. So it's almost entire, that is, it's entire except on s equals to 0 and s equals to k. And if f happens to be a cusp form, that is, if the zeroth coefficient is 0, then these two terms also vanish. So in that case, the completed L function is an entire function. Right? Okay, now what are the residues then? No, the residues of this. So this is defined as this, right? So what are the residues of this function at s equals to 0 and s equal to k? That's right. How do you know that? Well, because residue is linear. By that I mean that residue of, let's say, g plus h at some point, let's say z equals to z naught, is equal to residue of g at z naught plus residue of h at z naught. Since these two terms are entire, their residue will be 0. Now, what is residue of negative a naught over s at s equals to 0? We know that it's negative a0. What is negative a naught over s at s minus k? Sorry, negative 1 to the power k. Let me erase this. K over 2 a0 over s minus k. What is this residue?
SK.
No. No, first we are computing the residue at s equals to 0. Yeah, it's 0. Because in a neighborhood of 0, this function is holomorphic. Right? Okay. So therefore, residue of the computed real function at x equals to 0 is negative a0. Similarly, residue of lambda at s equals to k is negative 1 to the power k over 2 a naught. Yeah, this is the residue. And yeah, and furthermore we had another like functional equation, that is this. So how do you prove this functional equation? We just replace all the s by k minus s in our formula. So let's see how it changes. So this integral right here, if we replace s by k minus s, so how does this formula change? Okay, I think it's better if I write both the integrals because we have two integrals. The constant terms, yeah. If I replace s by k minus s right here, I get a factor of negative 1 to the power k over 2. Like, let's say the constant, let's first write the constant terms. So if we replace s by k minus s, what do we get? We get here negative a0 to the power k minus s plus negative 1 to the power k over 2 a0 over minus s. That's right. So, and this is basically negative 1 to the power k over 2 a0, negative a0 over s plus negative 1 to the power k over 2 a0 over s minus k. Right. So the constant terms carry a negative sign if we replace s with k minus s. How about the integrals? Let us write the integral. So the second integral is negative 1 to the power k over 2 times f of iy minus a naught y to the k minus s dy over y. And the first integral was f y minus a naught, then y to the s dy over y. Right? And if you replace s by k minus s, what do we get? This negative 1 to the power k over 2 f of iy minus a naught. And how does this term change? It becomes y to the s, right? dy over y 120 plus what about the second term? F of iy a0 y to the power k, sorry, y to the power k minus s dy over y. Now, can you see that these two terms differ by a factor of -1 to the power k over 2? Because k is even, so -1 to the power k will be 1. Right? So therefore, we prove our functional equation that was saying that lambda of f k minus s is equal to -1 to the power k over 2 lambda of s. Well, actually, the key purposes of introducing these completed L functions is actually making the functional equations look a lot cleaner. Because I think last time we've seen the completed zeta function, right? The completed zeta function was defined like this. Z of s was defined as pi to the power minus s over 2, gamma of s over 2 times zeta of s, right? And the functional equation for zeta was really long, right? But the functional equation for the completed zeta function is actually really simple. And we can see a lot of parallels in this and this. So yeah, so we have finally proved that if we form the L function of a modular form, although the definition looks like that the L function forgets the zeroth coefficient, but actually it's not forgetting anything. You can recover everything back. Okay. Yeah. Yeah. So now, I think a good closure for us will be to see some examples of linear transformations in the vector space of modular forms, right? Because we have seen that M sub k is a vector space. It's a finite dimensional vector space. So, of course, like you can write down how many linear transformations from Mk to Mk we have, right? So, this the number of linear transformations from Mk to Mk is what? If D is the dimension of Mk. So how many linear transformations we have? We have infinitely many linear transformations, of course. And those linear transformations are basically like D times D square matrices. Right? Yeah. But for our purpose, we shall not look at this like matrix picture. So we are going to define a linear operator on the space of modular forms. Then we are going to say that, well, yeah, this is indeed a linear transformation between spaces of modular forms. And those operators are actually really interesting to number theorists. For instance, have you heard of Ramanujan's tau function? So yeah, we have seen the weight 12 cusp form delta. That was our the only example we have seen for modular forms that vanished nowhere, right? And this can be written as like this. It's q1 minus q to the power 24 n the product of this. Okay, and of course it has a q representation that goes like a1q plus a2q2. So Ramanujan's tau function is actually this. So there was a famous conjecture, not a conjecture anymore, that is this tau function is multiplicative. The multiplicity of this tau function is proven exactly using the theory of Hecke operators. Hecke operators. What is that? We're going to define this now. Okay, so it's actually a family of operators, and yeah, so it's a linear map from mk to mk. So let's say f is a modular form of weight k, then tnf is also supposed to be another modular form of weight k, right? So it's a complex holomorphic function. So it's a function. So we are going to define that function by its inputs. So it is n to the k minus 1 sum of d to the minus k, where d runs over the divisors of n, sum of b equals to 0 to d minus 1, f of nz plus bd over d squared. Okay, so from the definition, it's clear that this is a linear map, right? But it's not very clear that this function we get in the right hand side, it's a modular form. It's not very clear from the definition, right? So yeah, we are going to prove that this is a modular form. So let us first look at how this Hecke operator Tn, how this Tn transforms the Fourier coefficients, right? So I'm going to use a little bit of different notation because, well, writing a fraction in the subscript is really difficult for me. So I cannot write a sub x over y. Okay, so that's why I'm changing the notation a little bit. Okay, so the theorem that says that if f is a modular form of weight k, then it has a q expansion that goes like this: e to the 2 pi I mz, and here am, right? So I'm writing am c of m. Okay. Then tnfz. So this also has a q expansion, and that q expansion is given by infinity gamma n of m e to the 2 pi I mz, where gamma n of m is given by sum of d to the k minus 1 c of mn over d square, where d runs over the divisors of the GCD of m and n. Okay. Yeah. So this notation is actually more convenient for me because writing a sub mn over d square, yeah. So let us try to prove this. Proof. So let me just copy this definition from here. Copy and paste it here. Okay, perfect. So this is, yeah, let's just write this f as the Q expansion. So T n, no, sorry, m equals to 0 to infinity, like everything else remains the same. except here we have e to the 2 pi I m nz plus bd over d square. Right? Yeah. And here we have a c of m, and everything else is the same. Yeah. Sorry. Okay. That's right. So now what do? We take this sum. This is the m sum, and this is the d sum. This is n over d to the power k minus 1. So you have another d term here. C of m e to the 2 pi I m nz over d square times 1 over d sum of, you have a b sum. Where did the b sum go? Yeah, yeah, there's a b sum. Sorry. Yeah, this b sum goes from b equals to 0 to d minus 1. And this is e to the 2 pi I mb over d. Yeah, I hope now it's correct. Right. So there was a b sum here which I missed while copy pasting. Right. So this b sum. Now, what is this b sum right now? Exactly. So, what is that? That's the answer is almost correct. So that's 0 when d does not divide m. When d divides m, this sum is not 0. If d divides m, this sum is actually d. Like all the terms are 1. Because e to the 2 pi I, it's 1, right? And if d divides m, then mb over d is always an integer. So then all the terms are 1. So this is 0 if d doesn't divide m. Sorry, let me write it again. So this is 0 if d doesn't divide m, d if d divides m, right? So you can combine this sum and this 1 over d term to write sum of m equals to 0 to infinity. And here I'm going to write d divides n and d divides m. Because the terms which, the d's which do not divide m basically contribute 0 in the end. So this n over d to the power k minus 1 times c of m e to the 2 pi I m nz over d square. Right? All right. So since d divides m, let's write m equals to qd. Okay. So then this outer sum is actually q equals to 0 to infinity. D divides n over d to the power k minus 1 c of qd e to the 2 pi I q n z over d. Right. Okay. Now what we're going to do? We are going to replace, we're going to basically replace d by n over d. if D runs over all the divisors of n, then n over D also runs over all the divisors of n. So this is a very common trick that we use. So this is the Q sum, this is the D sum. So this is going to be D to the power k minus 1, then C of Qn over D, then e to the 2 pi I q dz, right? And again, q is m over d, so let's replace that. M equals to 0 to infinity, d to the k minus 1, then c of mn over d square. There is this sum, d divides n, times e to the 2 pi I mz. And this is precisely gamma n of m. So we have proved that. So we have proved that if f has a Fourier expansion like this, then so does T and F, and they are related like this. All right. Yeah. Now let us revisit the definition once again. Okay, so this time since D divides N, let us write N equals to, let's say, AD. Okay, then what does this definition become? This is 1 over N D to the minus K, that becomes A to the minus K, right? And yeah, so this is, let me write all these conditions in under one sum. So A is greater than or equal to 1, AD equals to N, and B is in 0 to D. Okay. Now, does this the argument of f, the input f takes in this sum, does this remind you of anything? Any group action? Yeah. So this is actually, if we define a matrix like this, let's say if we call this A, then this term is actually f of AZ, right? So therefore, this term, we can rewrite this term as 1 over n, sum of a to the minus k, f of AZ, where the conditions are as before, that AD equals to n, then B is from 0 to D, and so on. Right? So this gives us the motivation to define some sort of transformation of order n. Transformation of order n. What is that? That is, if we have a 2 by 2 matrix with determinant 1, then we call that group SL2Z, right? But this time, let's say the determinant is n. Then under this matrix, so this matrix takes Z to AZ plus B over CZ plus D, right? So this is called a transformation of order n. Okay. And yeah, and also we can form the set of all those transformations. So let's gamma of n is equal to all the matrices A, B, C, D such that AD minus BC equals to n. So as usual, gamma of 1 is our favorite group, SL2Z. Also, these A, B, C, D, these are integers. So these are our favorite group, SL2Z. Gamma of 1 is our favorite group. So now we can define an equivalence relation uh, on gamma of n, and we are defining it like this. So we are calling A1 and A2 equivalent if and only if they are related by some SL2Z transformation. A1 is equal to, let's say, VA2 for some V in gamma of 1. Okay, so you can easily check that this is an equivalence relation. So, and we have a very powerful theorem which we are not going to prove. So that theorem has multiple parts. So first part says that in every equivalence class of gamma of n, there is a representative. And that representative looks like this: A0, B, D for D greater than 0. Okay. And the second part is actually more stronger. So that's actually stronger than stronger. Okay. So the second part says that if we mod out gamma n by twiddle, then this is precisely this, the set of all the matrices A, B, 0, D such that AD equals to n, D runs through positive divisors of n, and B is between 0 to D. Okay, and this this should look familiar because in this sum, AD equals to n and B is from 0 to D. Right. So using this theorem, we can basically rewrite our definition of Hecke operators. That is, Tn f at z is equal to 1 over n sum of a to the k f of az. Now where is a? A is in gamma of n modded out by the equivalence relation. Now, of course, there are like multiple. Yeah, so of course, this is just a representative of the equivalence class it is in, right? So we are only taking like these like good-looking representatives. So these are good-looking representatives because we really like these matrices. So these matrices are basically needed for our definition of Hecke operators. So yeah, this is this. Now, yeah, so this is our new definition of Hecke operators. And the theorem actually has a third part, and that part is really important for us. So that part basically says that, let's say if A1 is in gamma of n and V1 is in gamma, then there exists some A2 in gamma of n and V2 in gamma, such that A1 V1 is equal to V2 A2. Okay. And there is actually a second part to the second part to this third part. Okay. That is, if let's say AI is equal to AI BI 0 DI. So if these A1 and A2 are the good looking representatives we like, then also let's say VIs are alpha I, beta I, gamma I, delta I. Okay. Then like A1 gamma to A2Z plus delta 2 is equal to A2 gamma 1Z plus delta 1. So this is actually really important for us because, yeah. So in our first definition of a modular form, we define like this, that f of az plus b over cz plus d is equal to cz plus d to the power k f of z, like this, right? So this cz plus d term is actually this. So yeah. So using this result, we are going to prove that the Hecke operator is indeed a linear operator uh, in the space of modular forms. So the theorem states that TNF of V is that. So V is the matrix in our favorite group SL2Z is equal to gamma Z plus delta to the power K TNF of Z for all V is equal to okay. So this is basically proving the modularity condition for TNF. So, right. So let us write the new definition of Hecke operators we've seen. That is TNF of Vz is equal to 1 over n sum of a to the power k f of a v z, right? Now this sum runs over all the a belongs to gamma n modded out by the equivalence relation. Now, yeah. And by the third part of the theorem, there is some V2 and A2 such that A V1 equals to V2 A2, right? Sum of A to the power K f of V2 A2 Z. All right. Let's say, sorry, this is V. Yeah, let's say V2 is alpha 2, beta 2, gamma 2, delta 2. Then by the definition of a modular form, we get this is equal to gamma 2 A2Z plus delta 2 to the power k f of a to z. Is that right? So we get 1 over n sum of this a times gamma to a to z plus delta 2 to the power k. Now, what are we going to use right now? Like, which part of the previous theorem we're going to use right now? Like, does this term look familiar? Yeah. So, this is basically the term on the left hand side of this boxed formula. So, therefore, that is equal to the term on the right hand side. Right? So, what is the term on the right hand side? Sum of a2 to the power k, then gamma 1 z plus delta 1 to the power k. Right. Now we are basically done. Why? We need to check that, well, as A runs over all the equivalence classes, so does A2, because this sum is over A2 and A2 depends on A. So we need to check that, and that is of course left as an exercise. Exercise, check that A runs over gamma of n ordered out by the equivalence relation if and only if A2. Okay, you need to check this. So therefore, using this sum, we get this equal to 1 over n sum of tnfz, because we have it and this is. Okay. Right. No, there is no sum. I'm sorry. The sum is for the definition of Hecke operators. Yeah, this. So we have checked the modularity condition. Now we just need to check the remaining like conditions, that analyticity and bounded as the imaginary part goes to infinity and so on. Okay. Yeah. Now let us write the first definition you've seen of TNF. Okay. So what was it? It was like this. N to the power k minus 1 sum of d to the power minus k, where d divides n, sum of b equals to 0 to d minus 1 f of nz plus bd over d square. Now can you see that f is analytic on the upper half plane or holomorphic on the upper half plane? So TNF is holomorphic on the upper half plane. Can someone tell me why? Because it's the, so how many terms are there in this sum? There are finitely many terms, right? So TNF is actually a finite sum of holomorphic functions. All these are holomorphic functions. Therefore, TNF is also a holomorphic function. Right. Also, we have seen that TNF has a Fourier series that goes like this. Sum of gamma m m e to the 2 pi I mz. Right. Therefore, like TNF of I infinity is bounded. And that is nothing but gamma n of 0, right? So we have checked all the conditions for a modular. So therefore Tn is indeed a linear map from Mk to itself. Okay, does anyone have any question about this? All right, yeah. Now, since it's a linear operator, we can talk about its eigenvalues and eigenfunctions. Sorry, eigenvalues and eigenvectors. Yeah, but the vectors here are modular forms. So those eigenvectors are called eigenforms. So eigenforms of Hecke operators are really important in the theory of modular forms. Right? Yeah. Okay. So lastly, I can actually show a really cool theorem, then we can call it a day. And that cool theorem is that if m and n are co-prime, then Tm followed by Tn is equal to Tmn. And the proof goes like this. So proof Tn f of z is equal to 1 over n sum of a to the power k f of az, right? Sum is over a. Now, what if Tm of Tnf acting on z? So what is this? So for this m, we have a 1 over m sum over, let's say, b alpha to the power k. 1 over n sum of a to the power k. Then f of b a z. Right. So let's say a is ab0d and b is alpha beta 0 delta. Now what is ab? Alpha a d delta, and this is alpha b plus, sorry, no, this is, sorry, I need ba, not ab, ba. So yeah, alpha b plus beta d, right? Yeah. Now, since m and n are co-prime, if let's say some d prime divides mn, we can actually write d prime as some d times delta, where d divides m and delta divides n. So this can only be done because m and n are co-prime. Since m and n are co-prime. And yeah, and as d and delta run over all the divisors of n and m respectively, d prime runs over all the divisors of mn. Right? So therefore, as A runs over all the equivalence classes of gamma n and B runs over all the equivalence classes of gamma m, you can say that BA runs over all the equivalence classes of gamma mn, right? Therefore, this is equal to 1 over mn sum of A alpha to the power k f of BA z. And this is precisely Tmn f of z. And it has a really interesting continuation of what happens if m and n are not co-prime. I'm just writing the formula. Tm Tn is equal to, it's a sum of d to the power k minus 1 t mn over d square. D divides. Can you guess what does d divide? No, not LCM. Try to connect this with the result we just saw. That if m and n are co-prime, then Tm, exactly. So Tm Tn was equal to Tmn if m and n are co-prime. So this is d divides GCD of m and n. So if m and n are co-prime, then d must be equal to 1. So yeah. So if you want to learn more about Hooke operators, I have a very beautiful book that is written by Tom Apostol. Tom Apostol's Modular Functions and Dirichlet Series in Number Theory. Modular functions and Dirichlet series in number theory. So this book is really good for learning about, well, we have learned about modular forms, right? So there are some like generalizations of modular forms that is called modular function. Those are basically modular forms of weight 0. But we have seen that the only modular forms weight 0 are the 0 function, right? So the definition of a modular function is a bit weaker. So that's why they're interesting modular functions. So this book is actually really good. So you can take a look at this book for more references about these Hooke operators and eigenforms and so on. Okay. Okay, so now, yeah, any questions? Right. Okay, so then I think we can, yeah, I think we can end this. Like, thank you everyone for being with us for the last nine weeks. Yeah, and I don't have an emotional speech prepared. Yeah, okay, so that's all I think.